Hi, everyone. Before we start determining sample sizes, I'd like to discuss some more tech. For example, before, I expressed surprise that for this ridiculous confidence level, 99.9999%, uh, the confidence interval for P seemed almost reasonable, from 35% to 57%, basically. Uh, Nothing like 0 to 1. But actually, this shows how, for the standard normal Z, the tails fall off very rapidly. I mean, we get about 99% within 2.58 standard deviations of the mean, and we get almost everything, this proportion, within about 5 standard deviations of the mean. So it shouldn't have surprised me that we didn't have to go too far out to capture almost everything. The tails fall off very rapidly for a Z. So actually, these critical values were not that ridiculous, and these limits were not that ridiculous. Although it's true that if you put a whole slew of nines after this, then eventually these would get really ridiculous. And then maybe this could go negative below 0. This could go above 1. In which case you would truncate the confidence interval. A 100% confidence interval for P would be from 0 to 1, but Excel doesn't know that. So Excel might put a negative number here and a positive number there for a really ridiculous confidence level, even worse than that. So that's one comment. Now, what about simulation? You might look at all this and go, can't we just do computer simulations? Well, let's look at the Rossmann chance applets. The Rossmann chance applets, over here, statistical inference, one proportion inference. Now, before, when we were studying binomial distributions, we would assume a fair coin, okay? Let's say we flip it 500 times, right? And it turned out here that we got about 232 heads or so. And we can redo this in terms of proportions. So that would be about 46, 47% out of the 500 flips. Well, let's do this 1,000 times. We're going to have 1,000 people flip a fair coin 500 times. So you get this distribution for the proportion of heads, various values for p hat. And we might ask, so where would 0.46 be, right? And just by sheer chance, if the coin were in fact fair, how unlikely is it that we would get something as extreme as 46% when we're performing an experiment of flipping a fair coin 500 times? But bear in mind, we can't get a confidence interval out of this. So we have to try a completely different approach for a confidence interval. Okay, so what do? We saw that in our actual sample, we got 46% heads, 230 heads out of 500. So in our this applet, let's assume for now that the coin really was 46% heads. We have each of 1,000 people or 10,000 or whatever flip the coin 500 times, like we did. And then we get this dot plot for various values for p hat. Now, wait a minute, you say. You might be going, but here we're assuming that p, or pi, the true probability of heads, is 46%, or 0.46. And these are various values of p hat that we get. I thought that 0.46 was p hat, and we're trying to figure out where p was. Yeah, but remember, we don't know what p is. So we're basically assuming for now that that p hat, 0.46, is the true value for p, and we're asking, so based on that assumption, what would be the sampling distribution for p hat? And then we could pick the middle 95% of values, or the middle 90% of values, and use that as our confidence interval. So that's how you could do a simulation. You would grab the middle 90% of these values for p, right? You look at this dot plot, pick up the middle 90%, see what that range of values would be, and that would be your confidence interval. Based on a good simulation, you should get something like from 0.423 to 0.497. All right. So again, we're kind of thinking backwards. We assume that the coin was in fact 46% heads, so it matched our sample p hat, and we do a simulation based on that. I know it seems topsy-turvy, but that's a way that you can simulate in such a way that you can construct a confidence interval. So you could have a computer pick out percentiles here as your limits. The 5th and the 95th percentile would be the boundaries, the limits for your 90% confidence interval. Okay, next time, determining appropriate sample sizes.